Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. This will be the first part of a two-part video about multiparticle systems. Today we will introduce the momentum of a multiparticle systems and also how we treat them in general. Then we will see how a force on all that multiparticle system affects the system, and finally we will analyze a frame of reference that is really useful when analyzing multiparticle systems, that is center of mass reference frame. So let's start! Alright, let's imagine you have a system of particles, such as this one. Specifically, you're going to have n particles. Then you're going to attach a little label to each of your particles, such as, for example, this is particle
1, this is particle 2, particle 3, 4, this is particle n, because you have n particles, this is n minus 1, n minus 2, n minus 3, 5 over here, for example.
And each little particle, for example, let this be the jth particles, the particle number j, with j being a number from 1 to n. You're going to have that each of these particles is going to have a little mass mj, and it's also going to have a velocity bj. And you can see, I've tried to illustrate that the mass of the particles is going to be different, and also their velocities, their individual velocities, is going to be different. And we're going to symbolize that by this label in each of these quantities. Then we can see that we're going to have a momentum for each of your particles that is going to be P of j, and it's simply going to be mj times bj. And if we try to compute the momentum of the total system, it's going to be the sum of each individual momentum. That is that the momentum of the system is going to be equal to the m1 times b1 plus m2 times b2 all the way up to mn times bn. This is no other thing than the sum from I equals 1, or let's better use j as it's the label we've been using. So from j equals to 1 to j equals to n of mj bj, which is no other thing than the sum from j equals to 1 to j equals to n of each of the individual momentums. So we can conclude that the momentum of a system, the total momentum, equals the sum of each of the individual momentums. This is also known as the principle of superposition that applies in quantities such as momentum, not energy, but forces and other different quantities in physics. Great! Now let's see what happens when we apply some force to this system and we let it transform and interact with itself. We're going to have that there's an external force, F, well that's a P, sorry about that, F external on the J particle that is going to be applied to each and every of our particles. However, we are also going to have internal forces. if these are uncharged particles, we're going to have, for example, gravity pulling them towards each other. Therefore, we're going to have forces from each of the different particles to each other. So, for example, this is going to be the force from 3 and 2, the internal force. This is going to be the force internal of from 2 and 3. And you are going to have that every particle is being affected by every other particle in the system. In that way, we're going to define one quantity that is going to be Fj internal, and it is going to be the sum of the forces applied by each other particle on that one, our jth particle. So we're going to have the sum over k not equal to j from 1 to n, we'll omit that for simplicity, of each of these forces, or each of these internal forces, and that is the force that k acts on j. And we'll also define a external force that is going to be simply the sum of j equals 1 to n of f external j. From our Newton's second law of motion, we know that force equals dp dt. So if we are considering the total force, we need to consider the momentum of the system. And as derivative is distributive, we can see that this is the sum of j equals 1 to n of dpj dt, which is from j equals 1 to n the derivative, or the force internal plus the force external. So you have Fj external, which is this component we calculated over here, and you also have the change in momentum due to the internal forces. That is going to be Fj internal. We have already calculated the first quantity, that is F external, but we have yet to calculate this sum over here of internal forces. But first, note one thing. Newton's third law, it's really a statement about conservation of momentum, and we talked about that in our video that I pinned about there of Newton's laws. And that happens because F32 and F23 are really the same forces but in opposite directions, and that provides that momentum is conserved, and we'll see that that will mean that this sum is going to be 0. In general, we know that F32 internal plus F23 internal equals 0. Therefore, if we see and we expand this quantity, we see that it is, I'm taking that one, the sum from j equals 1 to n of the sum, and we are substituting this expression in here, of k not equal to j from 1 to n of fkj internal. And we'll see that for every j we select, there will be a k and a pair from the opposite ones that will cancel that first pair. We see that means that if j equals 1 and k equals 2, we will have a pair j equals 2, k equals 1 that will cancel that, in the same way we had over here. Therefore, we see that this is going to be equal to 0, which means that the total force that a system feels is just F external, because the internal forces do not contribute. It's just the sum of the external forces that each particle feels, but the internal forces have nothing to do with the variation of the total momentum of the system. Great! Now let's introduce the concept of center of mass, which will pave the way for your understanding of the next part of these multi-particle systems videos that will be available next week. In general, we are going to have this blob of particles. It can be for example, a cloud of gas, such that our system is more general, and we are going to still have these little MJ particles with this label attached to them, and we are going to define a reference frame and a stationary reference frame, and we are going to label it by S. However, this frame will not be very useful. The reference frame that we will usually use, and is the one that is mainly used in particle physics, is the center of mass frame. The center of mass frame is such that J equals to 1 from 1 to n of mj times r j equals 0. We can see that if we differentiate these quantities, we do a ddt right around here outside of the sum, mjrj equals 0. We may assume, well, ddt of 0, it's obviously 0. We see that this ddt will go through the sum and will go through the mj, because we'll assume mass is time independent, and will hit the rj, the different position vectors, and will give you a velocity. Therefore, this is going to be equal to the sum from j equals 1 to n of mj times bj. But this is no other thing than the total momentum of our system. Therefore, we see that this reference frame is defined in such a way that the total momentum of the system is 0. Now we want a way to calculate this center of mass frame with respect to our stationary frame S. In general, we can see if our center of mass is right around here, we can see that we have a vector triangle between our stationary position vector rsj and our center of mass position vector rcmj. And then we are going to have another vector, which is the one we are trying to find, that is going to be r, capital R, cm. We can see that for each and every particle, rsj, it's going to be equal to the sum of these two vectors, rcm plus rcm, j. Now, we want to sum over every single component of these mj's, and we will also weight this sum as with the mass, and you will see what happens. If we multiply by the mass of each and every object and we do the sum, we get the sum from j equals 1 to n of mj times r s comma j equals the sum of j equals 1 to n of mj, and RCM doesn't contribute to this sum, it's just a multiplicative out of it, and we have the sum from j equals 1 to n of mj r c m comma j. But note that the center of mass reference frame is defined in such a way, as we see here, that this quantity is 0. Therefore, we can cross this out and we can solve for the center of mass frame, the position vector, and we see that our CM equals this quantity. I'm going to step over here as it's easier to write, from j equals 1 to n of mj r s comma j divided by the sum from j equals 1 to n of the masses, that is the total mass. And that is in general how you calculate the position vector of the center of mass reference frame, which will be very useful to analyze multiparticle systems. That is all for today. These are some of the tools that will prove very useful to the analysis of multiparticle systems. I hope you liked it, and every doubt left you may ask them in the comment section and I will be happy to answer them. I'm really happy for the growth that the channel is having on the last days, and remember to follow us on Instagram so that you don't miss any of the videos, because YouTube notifications don't work so well. Remember to like the video if it was the case, and also to press the subscribe button and the bell so that you don't miss any of the videos, just in case YouTube notifies you. See you another day with more Physicawesome!